Our next talk is on inference of robust reachability constraints. And our speaker is Yanis Sellami.
Do not have any. Okay, great. So thank you for the introduction. So today I'm going to present to you our work on the inference of robust reachability constraints, which we did with my colleague in CEA. But let's not talk about inference of robust reachability constraints immediately. Let's start with a very simple, very boring example about program verification. So of course, programs have bugs. For example, here we have a very uninteresting program where you are going to feed into two variables A and B some values. And then it so happens that if you sum the two values and that the sum is equal to 0, then there is a bug. And of course, if you have a bug, you can exploit it with a vulnerability, and we need automated method to automatically detect such bugs. So there are automatic methods to detect some of these bugs. For example, symbolic execution, when you're going to explore the program path and find possible inputs that are going to lead to these specific cases. There are other possibilities, Pondian model checking, for example. And for example, here, this technique is going to tell you that if A and B are both equal to 0, then you have a bug. And as the technique is sound, so you have no false positive, you say, okay, so I have a bug, I'm very happy. If I am an attacker, I'm very happy, I can exploit this bug. But maybe it's not that easy. Maybe you're more in the context like this, where instead of feeding the two variables, one of them is uninitialized. Here, for example, B. And in these cases, if you still ask your symbolic execution engine, it's still going to do that, to say that triggering the bug is still very easy. You still have to put A and B equals to 0. But then as an attacker, if you try to reproduce or replay this bug, it's not going to happen. You're not going to be able to set the specific value for B, and so you're not going to be able to reliably trigger this bug. So, of course, this is a very uninteresting examples, but there are a lot of practical causes of unreliable assignments in programs, interaction with the environment, stack canary, uninitialized memory, etc. And so we need a methodology or a method to evaluate the practical replicability of bugs. So what has been proposed previously for this is a possibility is to use robust reachability. So what people do with robust reachability is they partition the input space between the one you can control as the user and the one that you cannot control as the user. So here you control A because you're going to feed it a value, but B is uninitialized, so you don't control it. And you focus on the finding unreliable bugs by setting a different type of quantifier between those variables. So you're setting an inexistential quantifier in the value you control and a universal quantifier in the value you do not control. And doing this, you say that in our case here, you're very happy because as B is uncontrolled, there is no value to feed in A that is going to reliably trigger the bug independently of the value of your uncontrolled input. So you're happy with this. You have extended reachability and provided tool for this, but maybe this is still not enough. Maybe you have this type of problem here, so the exact detail of the constraint isn't important, but you have memory copy function that does two things. There is a slow and a fast pass. So the idea is if you're slow, you can copy the bytes one by one, and in some cases, you can copy word by word, so several bytes each time. And the important part here is that the fast pass is buggy and the slow pass is not. So you have this program where you have a part that is buggy, a part that is not buggy. So of course, as there is a bug, your reachability constraint is going to tell you that this is a vulnerability. But as it depends on a memory alignment constraint, robust reachability is going to tell you that no, if you want to find a value that you control that is going to work independently of the value you do not control, so here are the exact addresses of your buffers, then it's not going to be robustly reachable. So you're not going to be able to reliably trigger this bug. But as you have an alignment constraint, memory alignment constraint, it's still going to happen a lot of times. So what you need now is the ability to characterize these cases that are in between simple reachability and complete robust reachability. So to do that, what we propose to do is to look for robust reachability constraints, which we defined as predicates on the program input that are sufficient to have robust reachability. So here, for example, you're going to set this as the alignment constraint. You have to have both your source and destination buffer, the addresses, aligned on 32 bits in order to trigger this bug. And if you have this, you have the advantage that it's already part of the robust reachability framework, and that it allows you for a more precise characterization. So now, the idea of our work is to find a method to automatically generate such constraints. So briefly, the contribution of our paper is that we propose an algorithm to be able to generate such constraint, which is based on a theory-agnostic abduction algorithm. And we propose a very efficient optimization in order to have this work in practice. So the idea is to find a predicate on your input memories that guarantees the reachability of a given prescription. So a bit of background on abductive reasoning. The idea is that you want to find a missing precondition of an unexplained goal. So there are already a lot of work that has been done on abductive reasoning, both in logic and for program verification. So either in theory-specific abduction settings or for specification synthesis. What we're interested in here is the theory-agnostic abduction algorithm that provides efficient procedures and genericity to handle a wide range of problems. So our goal here is to adapt such algorithm at program level to be able to generate a robust reachability constraints in this context. So now, how do we do this? It's fairly easy to obtain. So we have a baseline procedure that I'm going to present here. So we take, of course, our program and our target location or predicate we want to have in our program, and a memory partition between the inputs we control and the one we do not control. As we are going to be theory agnostic, we are going to base our generation on an inference language, which you can basically see as a set of candidate solutions we are going to try. And so what the procedure is going to do is first select a candidate, try to see this candidate is a possible robust reachability constraint. If it is, you have a solution, you're obviously happy. If not, you're going to try to obtain information from this failure case in order to obtain a more efficient generation. And how do we test that candidates are constrained? In order to keep our generic proposition, we are going to do an abstraction with Oracle for robust and non-robust properties that can accommodate a lot of different tools, such as symbolic execution, model checking, etc. So you get a baseline algorithm. The idea with this algorithm is that we have some properties depending on the properties that our oracles are going to have. So of course, termination, correction, and some completeness with respect to what we put in our inference language. And if we have all the good properties with our oracles, we can also have a minimality and a weakest constraint generation, which means that if you have the weakest constraint possible in your inference language, you will be able to generate it with this algorithm. So now, of course, as this is presented as an exhaustive exploration of an inference language, it's not going to be very efficient. So what we do is propose a set of strategies adapted from other work and improved with the genericity we have here in order to make this applicable in practice. So I'm not going to present all of them here, but some key points on what we are going to do. First, we can use necessary constraints. So the setup is we have a candidate. It's not a sufficient candidate, so it does not guarantee the reachability of our constraint. But maybe we can use an additional non-robust test to say that the constraint we tested is actually necessary in order to obtain our goal. So we will not be able to have our goal or our bug without this constraint being verified. So what we can do is add this constraint to the following constraint we are going to test. And by doing this, we can build a candidate solution that is going to be more precise, faster than if we had to do the exploration. This is something that we can do to emulate what you could do with unsat core usage, but in the context of generic oracles. Now, another thing you like to do when you explore inference languages is to be able to use and reuse counterexamples. So here, it's the same context. You have a candidate that is not sufficient, but what you say is that maybe from this information you can know that future candidate will be able to be eliminated from your candidate set without the ability to, without the need to test them. However, as we have a quantification, it's not going to be that easy to obtain this algorithm. So what we propose is to use an alternative property on the program in order to obtain counterexamples. And when we satisfy the satisfiability of the following constraint with those counterexamples, we are able to prune them from our set of candidates. So now, of course, we did some experimental evaluation of this. We tackled binary programs or compiled programs. So we did this with a restriction of our genericity with an implementation of symbolic execution and robust symbolic execution based on BinSec. We did a prototype and we evaluated this on two benchmarks from software verification and security evaluation. So the first idea, to give you just an idea on how we are able to generate the constraints. So we tackled fairly simple inference language with equality, disequalities, and inequalities between memory bytes. And what we show here is that we are able to generate more constraints that permit the robust reachability of the case, which is more than what you could characterize with only robust reachability. And that also among them, you can find constraints that are weakest constraints, which means that you have correctly characterized the whole set of inputs that permit to reach the bug you have set. So we did some evaluation to show which one of our strategies were able to improve or not our efficiency. What we show is that all of our strategies can improve the efficiency. But what's interesting is that each of the strategy we had actually impacted a different part of the algorithm. So some of them managed to obtain a candidate solution faster, some of them permit to reduce the size of the inference set, and some of them permit to get good candidates faster than others. And after that, what we did is some kind of vulnerability characterization in a security evaluation task. So here the idea was to have a fault injection benchmark, so mainly you evaluate a program that is not going to be executed correctly by the engine. You're going to fault the program during the execution, and by faulting the program, you're going to be able to change in behavior and introduce bugs. And what we wanted to do was characterize which of these introduced vulnerabilities were serious or not. So if we had only symbolic execution, we could find that 1,700 of these faults were introducing a potential formal vulnerability, but we were unable to see if they were serious or not. If we had only robust symbolic execution, we can find 118 cases that are very serious and very dangerous, but some of them are still serious. If we do a projection of the constraint with what we had, so to give mostly a proportion of inputs that are vulnerable, we see that with some of the constraints we generate, even more than 5% of the inputs are vulnerable. So we need to have this characterization. So as a conclusion, what we can say is that we propose a precondition inference algorithm that helps to characterize and improve the notion of robust reachability, that is built on an adaptation from theory-agnostic abduction algorithm, but applied at program level for will-exist-for quantified formulas. And we demonstrate its capabilities on simple yet realistic vulnerability characterization settings, so either in a software verification or security scenario. And what's interesting here is that we have preconditions that can explain the vulnerabilities that were introduced, so we can afterwards reuse in order to do additional work, for example, comparing vulnerabilities, understanding them, etc. So now I'm open to a question if you have some.
Hi. From a high-level point of view, it looks like you're doing some form of approximate quantifier elimination over the semantics of the program with the controllable inputs existentially quantified and the other ones universally quantified. Can you comment on the relationship between the two?
So the idea is that you can have if you have a relation, what you do not want to do is generate constraint on your existentially quantified constraints, because you are already going to explicitly specify them with the execution engine. But what you can have or need at sometimes is a link between the controlled and uncontrolled variables. So the algorithm is able to generate such constraints, but it's not perfectly adapted, because you are going to have some difficulty to prune some of these constraints if you put them in your inference language, due to the fact that you specify and explicitly characterize the controlled variables.
Thanks for the talk. That was really interesting. Once you've got a candidate precondition, and then you need to test whether this is sufficient. The property you're testing obviously has a mixture of existential and universally quantified variables. So does the procedure that you use to test whether this is sufficient have a mixture of, say, symbolic execution and traditional program verification? Because if you have no controlled variables, then you're doing like program verification. If you have no uncontrolled variables, then you're doing bug finding, like traditional bug finding. So how do you combine those two procedures?
So the actual tool we use does forwards these problems to the SMT solver. So basically you do a symbolic execution, you explore the path like you would for a direct symbolic execution, and then you universally quantify the part of the memory you have defined and uncontrolled. And you just send that to the SMT solver, and you get an answer from that.
So does this depend on there being a limited form of recursion in the program?
Not really. It depends on the ability of the tool you're going to use. But you can also reduce part of the algorithmic generation of your constraints if you want to. It's not.
Okay, thanks.
Thanks for the talk. It was really interesting. Robust reachability and symbolic execution and things like these, robust reachability applied to symbolic execution, this allows to have a whole bunch of optimizations when executing the program symbolically. How does this play out in this case? Can you use the inferred constraint while executing the program in order to prune part of the search space, or is it not possible?
That's what we would like to do, but it's not done actually.
Okay.
But yeah, it's part of the idea to go further, either to simplify the constraints you're going to send to the oracles, or to go inside the oracles to help them guide their search with some of the constraints you can generate.
All right. If no more questions, let's thank the speaker again.